Thanks very much to the organizers for the invitation to speak. I'm going to be discussing descriptive graph combinatorics, which is the study of classical combinatorial problems like coloring and matching, but where we put definability restraints on the types of graphs we consider and the witnesses also to their combinatorial properties. So if you have, for example, a Borel graph, how can you color it using a Borel function? And of course, some things end up being wildly different. A sort of typical example is there end up being acyclic graphs in this setting with very high chromatic number. Some things end up being the same, or at least not so different. And what I want to try to do over the 3 lectures is, or at least it's the theme that's going to unite all of them, is I want to study an analog of an idea in classical combinatorics where a really useful tool for proving results is figuring out good ways of building up graphs. So enumerating the vertices with some nice method or some way of arranging an induction or these kinds of constructions, and I want to find analogs in the descriptive setting that allow us to do similar things, good ways of building up Borel graphs. And hopefully in a way that lets us unify lots of different constructions in the subject that had previously been ad hoc, or provide a sort of more general toolkit for deriving results in the subject. So the rough outline of what I want to do over the next 3 days is based mainly on the type of definability we're going to consider. And for the first day, for today, I'm going to focus mostly on bare category. Okay, so things like bare measurable colorings of graphs, and let this lecture serve as sort of a slow-paced introduction with some nice examples. And in the middle today, I'm going to prove a nice sort of strong expanding sequence of points and graphs that's going to let me unify a bunch of previously disparate results in this setting. And so I'm going to talk about some relationships between paradoxical decompositions and matchings, some results about coloring, and we're going to try and address this theme a little bit of what ways can we build up Borel graphs if we're willing to throw out a meager set. So day 2, we'll focus on measurability with respect to probability measures. And the main tool that we'll develop here is one-ended spanning subfours of Borel graphs, modulo and null set. And the 2 main results that I want to derive on this day are some coloring results for measurable graphs, and then also moving a little bit to the setting of Borel equivalence relations, we'll be able to prove strong treeability for the class of planar graphs. So this is a very recent result from about a week ago. And it provides, or at least the technique arises from a nice duality arising in planar graphs. And it's a nice theorem because strong treeability gives you a host of other natural properties. For example, these groups will then have fixed price, and they're the first new example of groups with fixed price of cost greater than 1 that don't obviously arise out of Gaboriau's work from some time ago. And even some applications in pure probability percolation on planar Cayley graphs. And then finally, on day 3, we'll work in the pure Borel context. Okay. And then the main tool we'll use on the last day is Borel determinacy. And here, there are perhaps more open problems than solved ones, but many of the results I'm going to talk about, aside from combinatorial results, have things here to do with computability. So there's some old questions of Slayman and Steele and Tony Martin on the Turing degrees and Turing invariant functions, and we'll be able to translate those questions into questions about graphs, and in particular, how we can build them up in nice ways that avoid or contain certain sorts of structure. So that's the rough idea for the lectures. And now I think I'm just going to hop right in with an example of the sort of phenomenon that I want to study. So we're interested in combinatorial problems in the definable context, and I want to begin by giving you a nice little application by way of motivating something that I'll do immediately afterward of paradoxical decompositions to combinatorial problems. So let's start with the definition. So if A is an action of a group gamma on X, then a paradoxical decomposition of the action is a partition of the space X into finitely many pieces, and I'm going to separate those pieces into two finite sets, A1 up through AN and B1 up through BM, and group elements associated to each of those pieces so that if we translate these sets by these group elements, the sets A translated form also a partition of the space X, and so do the B translates. Sorry, the gamma I delta I partition X and the delta I BI partition X. Okay. And of course, the standard theorem about paradoxical decompositions is the Banach-Tarski paradox. And this is proved by letting the free group on two generators act freely on the unit ball minus the origin. Okay, and you can just find two independent rotations that, that give you this free group action. And then applying a paradoxical decomposition just of the left translation action of F2 on itself inside each orbit to find a paradoxical decomposition of the whole action. To find a paradoxical decomposition of A. All right. So, of course, when you act freely on the unit ball, at least, and I should have written it, sorry, with isometries, then you're preserving Lebesgue measure, right? And so it's clear there can't be a paradoxical decomposition of the unit ball using measurable pieces. And of course, the proof here, where we in each orbit apply this paradoxical decomposition of F2, uses the axiom of choice. On the other hand, we could ask what sort of other definability properties a paradoxical decomposition could have. And in fact, it's a result of Doherty and Foreman from 94 solving an old problem from the 1930s, that there's a bare measurable paradoxical decomposition. And I'll come back to that in a second. But before I do that, I want to point out a really nice application of this idea to matchings. And so I'll begin by explaining how paradoxical decompositions and matchings are related. So, given an action A, form the following graph. And let's call it G sub paradoxical of A and S, given finitely many group elements S. From our group gamma, whose vertex set is 3 disjoint copies of X, and where we connect edges up in the following way. So Ix is adjacent to Jy, if and only if exactly one of I and J is equal to 0. Okay. And there is a group element from our set S so that gamma dot x equals y, or gamma dot y equals x. Okay. So I have 2 copies of the space. This is going to be a bipartite graph where the first copy is connected always to vertices in the other 2 copies of X. And in this graph, perfect matchings correspond to paradoxical decompositions of the action. Okay, and recall that a perfect matching is a set of edges such that each vertex is incident to exactly one edge in the matching. Okay. So this corresponds exactly to a paradoxical decomposition using group elements from S. Okay, and here's the correspondence. Put X in, I need one more definition first. So letting S together with its inverses be gamma 1 up through gamma n. Put X into the set AI if 0, X is matched to 1 gamma I dot X. And X goes into BI if 0, X is matched to 2 gamma I dot X. Okay. So of course, the vertices of the form 2 and then group elements acting on X and 1 and group elements acting on X are all the neighbors of 0, X. It's matched to exactly one of them. And so this is a partition of the underlying space into the sets AI and BI. Right? And of course, if you take X and it's in AI, so you move it by gamma I dot X, then since every vertex of the form 1y has to be matched to something, there has to be some X that it came from. And that's why you have the translates also forming individually partitions of the space X. All right. Excellent. So, hence, the gamma I AI and gamma I BI both partition X. All right. So, it was an old question of Arnie Miller on his problem list whether there was a Borel analog of Hall's matching theorem. Okay, and I'll remind you quickly of the theorem. A locally finite bipartite graph has a perfect matching if and only if for every finite set in the graph the set of neighbors of S has size at least as big as S does. Okay. So this is obviously a requirement to have a perfect matching. On the other hand, it turns out to be sufficient in the classical setting. So the question, it turns out, had already been answered before it was asked. Laskovich in 1988 found a two regular, so every vertex has two neighbors, Borel bipartite graph with no Borel perfect matching. And the argument used some simple ergodic theory. On the other hand, these graphs, which can't have measurable perfect matchings because they would give measurable paradoxical decompositions, give an extremely strong refutation of this question. So, proposition, and this appears in a survey paper that I'm currently finishing with Elecos. For every constant k greater than or equal to 1, there is a Borel graph that's bounded degree. So that for every finite set, of vertices, the set of neighbors of that set is at least k times as large as S. But the graph has no Borel perfect matching. Okay. And the proof is just these graphs applied to measure preserving actions of the free group. So it is easy to check that for, let's say, f n with n greater than or equal to 2, in the Cayley graph of that free group, any finite set has a set of neighbors at least as big as n times S. Sorry? Yes, thank you. So take the graphs as before. Coming from measure preserving actions of Fn. All right. These graphs, right? So G, okay. So these graphs are spoiled for choice, right? The set of neighbors of any set is arbitrarily larger than S, and any constant you want to fix beforehand, but still there's no hope of finding a Borel matching or even a measurable matching. Okay, so this is just a nice illustration of the differences that can happen between combinatorics in the definable setting and combinatorics in the classical setting. But I want to move now to focus more closely on the theme that I was discussing. All right, so let's go back to this result I said earlier of Doherty and Foreman. And what I want to do is state a way of decomposing acyclic Borel graphs that implies a bunch of combinatorial properties of them, including the Doherty-Foreman result. So here it is written out. And this was in 94. let's get definable now. So every Borel action that's free of, let's just go with the case, the free group on 2 generators. Oh, this is an action where, for any non-identity group element, the group element moves every point in the space. So every free Borel action of F2 on a Polish space X has a bare measurable paradoxical decomposition. Okay, good. So let me introduce now this general lemma on acyclic Borel graphs. And from it, we'll give a very quick proof of this result and a few others. Oh, I should mention, by the way, that this idea, this duality between paradoxical decompositions and matchings, this is not our idea. This is just about as old as the study of amenability is. So it turns out if you have any non-amenable group, it's easy to prove that you can find some finite set of group elements so that if you take any finite set and apply those group elements, it grows in size by at least 2, a factor of 2. And that tells you that Hall's condition holds in this associated graph. And so there's a paradoxical decomposition. So this is a standard way of proving the equivalence of some of these definitions of amenability. And it's just applying that idea in the descriptive setting, which apparently we'd forgotten to do until recently. So here's this lemma, which I want to focus on today. So suppose G is a locally finite Borel graph that's acyclic on a Polish space X. Then there is a bare measurable function f on X sending X to itself, or f of X is a neighbor of X. With 3 different conditions. So first of all, for every X, there is an n, so that f to the n of X is f to the n plus 1 of X. Okay, so eventually each point reaches another point where it's self-mapped. Secondly, for all X, the inverse image of X minus itself, maybe I should move to the next line, is large. So in particular has size at least the degree of x minus 2. So this is the number of neighbors of x. And that's it. So I'll draw a little picture here. Eventually, any point is going to have to reach one of these self-mapping points. And until then, each point has a large preimage. Okay. Most of its neighbors map to it. Yeah. Question? Okay. So what's the lemma good for? The lemma is good for building up the graph in such the way that at each stage, you have lots of neighbors in the next stage bordering the points that you've already considered. Okay. So we therefore have sets A0 being the set of points x such that f of x equals x. And then we make inductively sets ai plus 1 being the set of points x such that f of x is in ai. And this is great for doing combinatorial constructions where you want a lot of neighbors at the next step because of this degree property, right? Any point in AI is going to have the vast majority, all but 2 at most, of its neighbors at the next level. Okay. So what I want to do now is give quick proofs of a bunch of things from this lemma, starting with Doherty and Foreman's result. Okay. By the way, it's clear that you can't have such a function that's measurable, at least if your graph is measure preserving, because this would be a smooth connected subequivalence relation. So, proof of the Doherty-Foreman theorem. Given a Borel action, A of the free group on 2 generators, associate the graph okay, and this needs to be free as in our theorem over there. So associate the graph on the same space where 2 points, x and y, are adjacent if some generator maps x to y. Okay, so this is an acyclic graph. Because this is a free action in the Cayley graph of the free group is acyclic. And it's 4 regular because there's 2 symmetric generators of the free group. Okay. And what we want to do now is construct the paradoxical decomposition. And I'm going to use yet another equivalent way of talking about paradoxical decompositions. So it suffices to construct bare measurable functions f and g. And I guess I've already used f in the lemma, so why don't I say g and h? On x, mapping each vertex to a neighbor. Okay, so another way of saying that is that g and h are subsets of the graph G. And their ranges partition the space. Okay. So again, I'm limiting these functions that I'm about to construct to being one of the neighbors in this graph, the application of one of these four generators, or their inverses. Right? And they both have domain the whole space, but their ranges are disjoint and partition the space. So the graph is on the vertex set x. That's the space on which A acts. The graph G is defined by saying 2 points are adjacent if a generator sends one to the other. Yes, sorry. I should have said at the outset, as a set theorist, I view a graph as a symmetric, irreflexive relation. Yeah, so it's just the relation. I'm not thinking of it with any more structure. Yeah, right, it's the edge set. Good. Okay, so is it clear that such a G and H would give you a paradoxical decomposition? Yeah. The notation is concise, if not edifying. Yeah. Well, two things called G. All right, so what do I want to do? I want to take this function f that I was going to use. So let f be as in the above lemma. And AI is defined above. And construct these two functions, G and H, in countably many steps corresponding to the sets AI. Okay, so first, let me say what we're going to do at step n will ensure that AN is included in the domain of G and H. Okay, and A sub n minus 1 is in the range. Okay. So what do? I might as well assume there's a Borel linear ordering of my underlying space, since all polar spaces are isomorphic, and there are polar spaces with Borel linear orderings. The union of their range, yeah. Yes. Okay. So for, first of all, x in A0, put g of x, the least element of f inverse of x minus x, and h of x, the greatest element. Okay, so there's at least two things in that pre-image that are not equal to x, so I have at least two choices to start off with. And to finish, we just keep doing the same thing. We have at least two options to map x2 with g and h disjointly. The only thing to make sure is that their ranges partition the space. And so I need to add one more condition at subsequent steps. Oh, just having fixed some Borel linear ordering of the underlying space. Yeah, it's just a cheap trick to avoid talking about uniformization. Yeah. So for x in an plus 1, if f of x is not already in the range of G, disjoint union the range of H, put G of X equals F of X, right? And let's say H of X again, the greatest element. Of that set. Okay. Otherwise, define G and H as before. And that's it. Okay. And just inductively, all the conditions that I want are satisfied iteratively in the construction. Good. I'm going to stop being so precise with proofs for a minute, but let me mention a few other corollaries. Of this way of decomposing graphs in a bare measurable way. Okay, and I should probably mention an attribution to this. This is also in this survey paper that'll appear soon. A0 is going to be covered when I consider A1. And when I'm working on A1, I'm going to consider some x in that set, and if f of x, so that original element of A0 that it's mapped to, isn't already in the range, it's going to be mapped to by G, by my definition. And then iteratively for all the rest of the steps of the construction. So something very closely related, which is actually what inspired this whole sequence of theorems that I've given you, was a theorem of Clinton Conley and Ben Miller from around 2010. Acyclic Borel locally finite graphs. of degree at least 3 everywhere, have bare measurable matchings. Okay. So of course, the graphs that I made to talk about matchings versus paradoxical decompositions aren't quite acyclic. They have these 4 cycles where the 2 different copies of the space both want to connect to the same points in the other copy. Okay. But it was sufficiently close to wonder if there might be something going on with what was happening here and what was happening here, and the result was abstracting out this underlying principle. And I can just tell you the quick idea of how you prove this from the lemma. It's just construct the matching piece by piece, starting with A0 again. And you always have at least one thing in the preimage to match to if you aren't already matched. So very easy. Okay, here's another theorem of Conley and Miller from around the same time when they were working on bare measurable combinatorics. Oh, why the degree greater than or equal to 3? That's so you have at least one thing in your preimage which has your degree minus 2. Yeah. And Laskovich shows you can't do it with degree 2. Every acyclic locally finite Borel graph has a Borel 3 coloring. Okay. So there's this general question of sort of how badly can these notions of definable coloring and classical coloring separate? And in the acyclic case, bare measurable colorings, at least for locally finite graphs, turn out not to separate very much at all. It is an open question for general, let's say, locally finite Borel graphs, not acyclic ones. What are the possible pairs of the ordinary chromatic number and the bare measurable chromatic number? Okay. And they have some results addressing this recently. The proof of this from this is, again, a really easy argument. You have at most 2 things. Oh. This is wildly false when you put Borel. Yeah, everything today, bare measurable except for the very beginning. Okay. So just color the vertices in A0, A1, A2 iteratively. At each point, you will, when you're considering some point in AI, you will have colored already at most 2 of its neighbors, right? So you have a 3rd color left. And you need to be very slightly more careful than that, but that's why this works. Another proposition. Every Borel locally finite acyclic graph has a bare measurable decoloring, de-edge coloring. Where D is the sup of the degrees of the vertices of the graph. Question? Oh, my handwriting's deteriorating, sorry. Every Borel locally finite acyclic graph of degree at least 3 has a bare measurable D-edge coloring where D is the sup of the degrees of the vertices in the graph. All right, and again, just apply the lemma. So I want to give you some idea of how this is proved. It's pretty short, and again, Yeah, the lemma now, right? Everything else on the board is a corollary. Sorry? Oh, okay. So a proof of the main lemma from today. Okay. So I want to set up a situation first. We've been considering locally finite acyclic Borel graphs, so I'm just going to fix one for what follows. So fix G, a locally finite acyclic Borel graph. Let y be countable. And let p sub finite comma g of x and y be the finite partial functions from x to y. Yeah, just some countable set. Nothing to do with anything here, yeah. Yeah. I might want it finite, I suppose, which is why I don't have omega there. But yeah, I might as well have it. So p sub finite comma g is the set of finite partial functions. From x to y with connected domains. Yeah, connected in the graph G. All right. So next, let Blackboard bold P, a subset of these finite partial functions, be Borel. The way you should be thinking about this right now is that I want to construct some bare measurable function on the vertices of the graph. And P should be the finite approximations that I'm going to allow. Okay. And of course, all the power in the lemma I'm about to state is going to come from choosing the right P. I'm going to say, basically, assuming the obvious extension condition that's required, you can find a Borel function that's an increasing union of partial Borel functions made out of pieces of P. Yeah, I'm trying to build the F in this lemma, but it's easier, I think, to decompose the proof here into a lemma and then an application of it. There's something very general going on. Okay, in fact, I've put on the board a few different bare combinatorial constructions. Of course, there's many more in the literature. The lemma I'm about to state is sort of reproved often in each of these papers. This is sort of a folklore theorem that's been proved by 15 different people at least. This is a generalization of generic hyperfiniteness, for one thing, which was proved independently by Horth, Kekris, Sullivan, Weiss, and Wright, and Wooden. It shows up, in a little bit more decorated form in these constructions. Doherty and Foreman already had the same idea in their paper, and so I'm just abstracting out the stuff they have all in common, and then you can apply it in each of these cases by picking a particular P. Though it turns out that getting yourself this with a particular P already gives you enough power to do a lot of stuff. that you want to do. So one more piece of notation. F sub p now be not finite, just arbitrary partial functions from x to y. Yeah, exactly. So that for every connected component of your graph restricted, let me give a name to these finite partial functions. So for every connected component of G restricted to the domain of F, I want to call this F because that's what in my head, sorry. But we're going to construct that F by picking a particular P here. They're going to be the same F. All right, so G restrict to the domain of F has F restrict to C, one of these partial approximations you're allowing. All right. So that's the setup. Here's the lemma. And maybe we can leave that up there and work here. No, these are arbitrary. Yeah. And I'm going to make a Borel function on the whole space as an omega sequence increasing of elements here. Yeah, exactly. So these are functions on the whole space that are made piecewise out of little p as their connected components. Yeah, exactly. So C must be finite. Yeah. Nope, C is a connected component of G on the domain of F. And if you restrict F now to that connected component, it's finite, and the function on that set belongs to the set of finite approximations P. Okay. Yeah, so I think I understand now the confusion. I'm about to state another lemma. I'm not working yet on the proof of that. Suppose, okay, so we've fixed all this stuff for the context of this lemma. Suppose for every function G in the set F sub P, and for all x in the underlying space of my graph, there exists some extension of G so that x is in its domain. Okay. Then we get the total function we want that's approximated using pieces from P. So then there is a sequence of partial Borel functions F0, F1, and so on, all of the type we're considering. So the domain of their union is comeager. And G invariant. So this is the abstract idea that's been hiding behind a lot of these bare measurable constructions. Oh, its domain is a set of connected components for the graph. All right. So I want to at least sketch a proof of this. And it's going to rely on one Borel coloring fact, which I'll just black box. So let the UIs be a basis for X. And we construct, starting with the empty function, this sequence to have the following property. We construct fi plus 1 so that its domain is co-meager, or non-meager, sorry, in the ith basic open set. And of course, that takes care of the domain being co-meager at the end of the construction. Next, I want to consider the space of finite sets to which I can extend the function f sub I in order to consider how I'm going to make f sub I plus 1. So let square brackets g to the less than omega be the space of finite g-connected sets. Okay. And let me have Z be the set of finite S in G to the less than omega, such that there exists some G prime extending Fi and S is a connected component of the domain of G prime. Okay. So it's the set of finite possible extensions I could make to Fi, or at least their domains. I just defined what it is. It's finite partial functions from X to Y. No, it's all of them. It's yeah. Yes. Yeah, I'm sorry that wasn't clear. I'm just using that concept so often I wanted a name for it. Yeah. All right. So here's the black box. Theorem, and this is Kekris-Miller. And topics and orbit equivalence. If E is accountable, or let's say an equivalence relation that's Borel. On some Polish space X. With countable classes. Then the graph G sub I on e to the less than omega. So these are the finite sets that are all E related. This is the intersection graph, where R is GI related to S. If R and S are distinct, and have non-empty intersection, no, he's just an equivalence relation now. I'm going to apply this. Yeah, Yeah. Right. Because of transitivity. Yeah. Right. Yes. They're the same. It's a subset of X. Is this? Yes. Yeah. E something. Yeah. Let's do this. E-related points. Yeah. Good. Right. Okay. I mean, viewing E as a complete graph in each connected component is the same thing as we have up here. Okay. So that's the graph, the intersection graph. GI has a Borel coloring with countably many colors. Okay. Good. So the reason this is useful as a black box is the following. Thus, we can partition Z into countably many sets coming from colors in a way that I'll say in a second. Which set? Yeah. It's the set of finite subsets of X. Yes. Well, they form a connected component. They're connected. Yeah. Okay, so we can partition Z into countably many Borel sets, Z0, Z1, and so on, where R and S and Zi that are distinct are pairwise of distance at greater than 1. That is, the closest point in R to a point in S has distance 2 or above from each other. Okay. So the reason you can get this is you just take Z, and instead of coloring elements in Z, these things, you color them union their boundary, so you have a little bit more space. And now you take different color sets coming from this coloring here, and that's going to partition Z then via the different colors into these sets that are disjoint, even when you take the one neighborhood around these different sets. Our extension assumption on this Blackboard bold P that we are using tells us that every point in the space is in some element of Z. Right? We can extend to include any element of the space in our function. Yeah. Yeah, so this is a completely... Mm-hmm. Yeah. In the original graph G, applying yes, all sets of vertices. Yeah, correct. The types are different between GI and G. Vertices in GI are finite sets. Yeah. But we're using this graph as a vehicle by taking color sets for the intersection graph on those sets to separating out Z into these discrete pieces. Okay. So, one of the sets union S in Zi is non-meager in UI. That's clear, right? Because let's let K be different than I. We can extend to put any point in our space into Z, and so any point appears in some finite set in Z and hence in one of the Zi's. Right, so every point is represented as you take these unions over these Zi's, and hence we have this non-meagerness. So by uniformization, we can extend Fi plus 1 to have domain the same as the domain of Fi, but then union all these S's in Zk. Okay, which is non-meager in UI. So the union over this set. Excellent. And we're uniformizing over possible extensions that are compatible with Fi, right? There's countably many of those things because Y is a countable set. This is finally where we're using the countability of Y. So a uniformization of that set tells you how to extend to make a function which is allowable in this scheme. So that's it. I mentioned that I haven't addressed G invariance. I have comeager domain. G invariance follows by general nonsense. So you could change the topology at the beginning so that you don't lose any comeager sets. But on the other hand, the graph is generated by involutions that are homeomorphisms. Okay. The last thing I'll say is that to get this original lemma from this one, I just need to pick the right P. So I'll just tell you the definition of P since we're out of time. It's the finite partial functions so that for every x in the domain, after iterating finitely many times, you reach one of these fixed points. So it's just built into these finite partial functions. That gives you property 1. And the second property is that if you have an x and it has at least 2 neighbors in the domain of this element of Blackboard bold P, it's also in the domain of P, and it has at least degree minus 2 preimages. and that's ensuring the second condition. And those two things together automatically imply these two properties. What's left is the finite combinatorics to establish this extension property. But that's a paragraph of easy work. All right, I'll end there. Thanks very much. Yeah, okay. So, exactly. You can parameterize functions that take x to one of its neighbors by some countable set of involutions generating the graph. And so, yeah, you make that translation so that you can regard functions sending points to their neighbors as functions to a countable set. Yeah.
Is there a finitely additive probability measure on the Borel subsets of the unit sphere, which is invariant under the rotations, which is different from Lebesgue measure?
That's an excellent question.
Unbiased Rousiewicz problem. If you say on the Lebesgue measurable sets, then Drinfeld and Margulies and people like that showed that the only one is Lebesgue measure.
Right.
But you're biasing that by asking about the Lebesgue measurable sets. So if you say the Borel subsets, you get an unbiased version.
Yeah. I don't think I have anything to add to that problem. But
okay, it's a question about paradoxical decompositions, which is why. Okay.
Yeah. There are some variations which still remain very much open related to what we've done here. Paradoxicality, bare measurable paradoxical decompositions for actions of non-amenable groups in general remain open, for example. So does the circle squaring problem in R squared, where you don't have such a convenient F2 action.
Yes. Wait. No.
So in this definition of P, can you repeat it again? What P was?
Yeah. Okay. So the P that you use to conclude the lemma at the top is functions with the first property. So even though they're finite partial functions for every x in their domain, after iterating, eventually you reach a fixed point.
A fixed point of what?
So for every n, there is an x, so that f to the n of x is f to the n plus 1 of x.
No, but you're trying to construct this function f.
Sorry? It consists of finite approximations that have the same property. And then the second property is that you want to make sure there's always room to keep expanding these preimages. And so you say if you already have more than one neighbor adjacent to you, you're already in the domain of the function, and you have this large preimage, at least your degree minus 2. And then it becomes finite combinatorics just to settle this extension property holds true. Yeah, the nice thing about this lemma is that it takes bare measurable constructions and it converts them into the finite combinatorics of finding an appropriate P here.